Welcome back, my dear students. In last class, in previous classes, we started module 2, second chapter. There is a compaction. In that compaction, various headings we already studied. For example, definition, standard and modified property test, factors affecting to the compaction, and properties affected by the compaction that we studied. Zero air wide line and compaction energy. These all concepts we studied. Now we are going into the next chapter, that is a field compaction control. This field compaction control means, say in previous classes we studied only the laboratory experiments. Means if you bring the soil to the laboratory, how you compact and what maximum density you are going to achieve, and how much water content you add to get the maximum dry density. These all things you are going to study in the laboratory. But the study in engineering, the study will not restrict to only laboratory. Means you need to take that soil to the ground, and there you need to achieve whatever the density you got in the laboratory, right? Therefore, there are some factors which we are going to consider when we go to the field. Means just you think that this is a field, and their embankment you are going to construct. This is the ground level, and first you will bring the soil here, and after that you level the soil, and after that by using some bulldozer or otherwise some heavy vehicles you will bring, and they will be moving on this one, and they will compact this soil, right? This you might see. Now this soil is compacted. The question is whether this compacted soil is achieved maximum density or not. Okay, that question arises. Or to achieve this maximum density, we need to add some water. You might be seeing first they will put some water, and after that the rollers will move. Then how much water we need to put, or otherwise how many rounds of these rollers we need to make to get this maximum density, that we need to observe. Or otherwise after 3 rolls or 5 rolls or 5 rounds of rolls, then you need to check the density. Then you will come to know whether that maximum density is achieved or not. This control we need to do in the field, that is called as field compaction controls. It is extremely important to understand the factors affecting compaction in the field. In the laboratory, the factors are different, that we studied already. But in the field, only 3 factors are there. They are very, very important. The first one is placement water content. Placement water content means how much water you are placing on the ground to compact. That is called as a placement water content. Then the type of equipment for compaction. See, we have a different type of soil. We have a clay soil. In that clay also we have a high plasticity, low plasticity clays. Silt also high plasticity, low plasticity clays. And sand is there. In that sand also we have a 3 type of sand: coarse sand, medium fine sand, and very fine sand. Okay, like that. And gravels are there. In that gravel also coarse gravels are there, fine gravels are there, medium fine gravels are there. Therefore, which type of soil is there on the ground, based on that you need to select the instrument you are using for compaction. That we are studying in the next this one video. The number of passes based on soil type. See, based on the soil type you are going to decide number of passes. Number of passes means if this is the length of the soil where you want to compact, then that roller will be there. This roller will move how many number of times that has to pass on the ground. That is called as number of passes you need to decide. That will be decided based on type of soil and degree of compaction desired. Degree of compaction desired is nothing but dry density which you want to achieve on the ground. Okay, therefore these 3 main important parameters are there that will control the compaction in the ground. See here, placement of water content is the water content at which the ground is compacted in the field. That is the water content at which ground is compacted in the field, not in the laboratory. That is the water content. But of course, this placement water content, a rough estimation will be done in the laboratory only. In laboratory, we'll come to know that at this water content, we are going to get the maximum dry density. That much of amount of water you need to put. Okay, it is desirable to compact at or close to optimum moisture content achieved in the laboratory, so as to increase the efficiency of the compaction. Okay, therefore whatever the optimum moisture content OMC you are observed in the laboratory, that much only water you need to put in the ground. Okay, however in certain jobs compaction is done lower than or higher than the OMC. Sometimes it happens, for example, the OMC is 22%. It means that at 22% you are going to get maximum dry density. But in the field we will not put 22% exactly, we will put 20% or 18%. Why this we are going to do? Because the ground may absorb the moisture from the atmosphere, or there might be a rainy season, and because of the rain some water will be flowing on the ground, and that will take care of the rest percentage of the water. Okay, sometimes it happens like if it is a very dry area like Raichur, Gulbarga, Ballari, and there, there that is a dry area, there you will put more than the OMC. If OMC is 22%, you need to put 25% of water, because of the hot climate the water may evaporate. Therefore, by considering the some climatic conditions, some other conditions, you may add 1% or 2% more or less than the OMC, that is a water content. Okay, where to add more, where to add less, that there are some examples I draw here. That is a highway embankment. Highway embankment, okay, for example, if this is a ground, and if you want to make some elevated ground, then you will put some soil here. Above that you will put a pavement and you will make a highway, and this highway you are going to compact it, and this is called as highway embankment. This is compacted dry of optimum. Dry of optimum means already compaction curve. In this compaction curve, this side is the dry of the optimum and this side is the wet of the optimum. They are saying that this all highway embankment must be compacted dry of the optimum to achieve high strength. Strength is very important parameter when you come to this highway embankment. Therefore, in our last class we already know that is the shear strength in the dry of the optimum will be more than the shear strength at the wet of the optimum. Therefore, to get the high strength you need to compact dry of the optimum. Low volume compressibility, this is also a quality at dry of the optimum, and good resistance to the deformation. Therefore, we have these three very important parameters. That's why the highway embankments are compacted dry of the optimum. That you need to remember. Then earth dams compacted 1 to 2.5% less than the OMC to reduce pore water pressure developed. That earthen dams will be there. This is the dam. You are going to restore water here. Okay, this is made up of soil, and the layer by layer you will put the soil and you will going to compact the soil. But to compact this one you add some amount of water. Here they are saying that the earthen dams compacted 1 to 2.5% less than the OMC. Why? Because there might be a seepage from the water. This water may pass through the earthen embankment, therefore the water content will definitely increase. That's why you need to compact it lesser than the OMC. In later course may increase, that water content of the soil may increase and you may achieve the maximum density. Then the cohesive subgrades. Cohesive subgrades means subgrade means this is a road, then road will be having some wearing course, and below that you will put some soil and you will compact, and you will excavate some amount of soil, and the ground, this ground is called as where you are going to put the subgrade and some wearing course and all, that is called as a subgrade. This subgrade, if it is a cohesive means if it is a clay type of soil or very fine soil, then under pavements compacted wet of the optimum to eliminate the swelling and shrinkage, swelling pressure upon the submergence. Okay, upon the submergence they are telling, means sometimes the water table may increase here. If the water table is increased, then this will be submerged. If that happens, then there will be more water content and there will be swelling, and swelling pressure will develop. To reduce that one, we need to put a wet of the optimum. Then the last one is impervious core of the earthen dam is compacted wet side to achieve low permeability. See the earthen dams, as I told, this is the earthen dam. Here I told this earthen dam, inside one core of the earthen dam will be there. This is also made up of soil, but this is compacted wet of the optimum and this is compacted dry of the optimum. That you need to remember. Okay, the dam is compacted wet side of the optimum, and why? Because the permeability should be low. Here water should not pass through here, it should go like this. Why the water path should be like a longer path, why it should pass like this, that you are going to study in the next semester. Their seepage analysis we are going to do. Okay, and greater safety against the cracking due to differential settlement. Okay, wherever you find the differential settlement, there you need to go for wet side of the optimum. Okay, these are some examples how this water content OMC is controlled based on the field application. Now next very important concept, now the compaction needle or Proctor needle. The Proctor, that fellow, that scientist who invented a standard Proctor test and modified Proctor test, they were done in the laboratory, but here to get the density achieved in the field, say for example this is a ground, and on this ground how much density is achieved, how to measure that one. Every time you cannot make a core cutter here and bring the soil to the lab, that is not possible. Therefore what you need to do, you need to take this compaction needle. This is also called as Proctor needle. This needle will be having some needle point here, that is called as interchangeable needle point. Means what? You can remove this and you can put another needle here based on type of soil. For example, if you are going for the smooth soil, smooth soil, then the needle size will be different, like that. Okay, this needle can penetrate inside, it can go like inside, and this will be, this is a handle. Exactly, it will be like this. This is a ground, and that needle will sit like this, and above that one needle point will be there, and there will be some arrangement here, and that will be connected to some handle here. This is just like a cycle pump. You know the cycle pump, some when you push this one, it will go inside, means this plunger will enter inside this pump, you know, that like that only it will be operated. See, what you need to do is, in the laboratory, first you need to use the Proctor needle that we have in the laboratory. I will show you when you come offline. Okay, see, I have a mold here. This mold is compacted for 1.5 gram per centimeter cube density and with some water content, OMC. Okay, this is compacted 1.5 gram per cc. Now here you need to put that needle and you need to observe the resistance by the needle. That resistance will be measured here, some calibrating, some readings are there here. Based on that reading you are going to read that one. Means 1.5, this is a resistance, this is the resistance. Okay, this is density achieved, and after that you take another mode, there you achieve 1.6, then again get the resistance 1.6, this is the resistance, then 1.7, 1.7, this is the resistance, then another mode 1.8, then 1.8, this is the resistance. Like that you get a various densities and various resistance, and after that draw the graph here. This graph is called as the penetration resistance graph. Okay, here they have shown in on the one graph only, or otherwise you can draw one separate graph. That separate graph will be like this. As the water content increases, dry density, that resistance decreases. Okay, resistance decreases because water content added means what? The soil becomes smooth, therefore resistance will be decreases. This graph you will get it. Now what you need to do? This needle you need to take and go to the field. See, this is the field where the people called you to check the density. Then put that needle here, and after that by using this handle you push it. When you push it, then some resistance will come and read the reading, and whatever the reading you are going to read, that reading you bring it and check where it is. This is the reading which is read in the field, and correspondingly you read the graph, and you will get the density, over. Means you come to know instantly how much density is there in the field by using Proctor needle test. Okay, now this is all about compaction needle and how we are going to control the compaction in the field. Okay, very important thing. Sometimes even core cutter also we will do, like in laboratory we will get a dry density maximum dry density that we will call gamma d max, gamma d max. Okay, this we get in the lab, in the laboratory, and we will go to the field and we do the core cutter test. Core cutter test I already explained in the first chapter. Then by doing core cutter test you will get a bulk density. By knowing the water content you can get the dry density. This is the dry density of the field. This is dry density of the field. Then we need to take the ratio, that is called as relative compaction. That is called as relative compaction. Relative compaction. This relative compaction means that gamma d of the field divided by gamma d max in the lab. Then whatever the answer it comes, that is called as a relative compaction. This answer, this relative compaction, if it is 1, the answer if it is 1, then what it indicates? It indicates that the field density and the maximum laboratory density both are same. That is very good soil. Good compaction is done. Okay, if it is a 0.5 or less than 1, then the density whatever the laboratory is there, that is not achieved in the field. Therefore, Indian standard IS code suggests that this relative compaction must be in between 0.95 to 1. Okay, in that only it will be there. Means the field density must be achieved 95%, more than 95% compared to the lab density. Understood now? Thank you very much. This is all about compaction. Next we will go and understand what are the equipments available in the market to compact the soil, field compaction. Thank you.